Hello, my name is Mariana Lima. I'm halfway through my PhD at the University of Brighton, and I'm happy to be here and giving this talk. And today I'll talk to you about the impacts of recent climate change on seagrass carbon sink potential, which is part of my preliminary results from my PhD. If you believe it or not, this background picture here is actually one of my study sites in the UK. So it's a seagrass bed in the UK, and it's in Langston Harbour, which is one of my study sites. So just a brief outline of my presentation, so you can follow through and know when it's about to end. This here is also a little bit of my seagrass that I've been analyzing. So an introduction. In the UK, we don't have a very big diversity of seagrass species. We mainly have Zostera, Marina, Enolti, and Rupia species. But in recent studies, it's been assessed that the Zostera, which is the most abundant species in the UK, has been declining over the past years. And some of the main threats that have been responsible for this decline are physical damage caused by dredging or anchoring, the excess of nutrients upload, and increase in turbidity conditions. Some of these factors can be caused by climate change or enhanced by climate change. So with climate change, we are predicting a sea level rise in the southern region of the UK, with land subsidence coupled with it, and that's where I am assessing where my study sites are located. And we are also expecting an increase in sea surface temperatures, which will be related to a higher availability of light, because the seagrass will need a higher availability of light for higher respiration. We are also expecting changes in precipitation patterns, and this could bring higher levels of turbidity because of storms clusters. Because of these potential impacts of climate change on seagrass, the overall aim of my project is to assess how carbon sequestration and storage in seagrass ecosystems in the UK have been influenced by recent climate change. So in order to do this, I will assess carbon storage and sequestration rates in my study sites. I will look into above ground and below ground biomass, and also carbon stocks in the soil, organic carbon in the soil. And I'll also provide a first assessment of the impact of climate change events, possibly related climate change events, on seagrass carbon storage and sequestration rates in the Solent region in the UK. So in order to do this, I will be calculating carbon sequestration rates, and I will be analyzing a possible correlation between the dates of sequestration rates in the sediment and extreme weather events. Also with occurrence of floodings and storms and sea level rise, anything that could be related to climate change. So my study sites, this figure here shows a distribution of Zostera, Marina, and Enolti in the UK. And my study sites are here in this southern part of the UK, what we call the Solent region. So the Solent region has very interesting characteristics. It's very prone to flooding. We've had a lot of historical flooding events in this region. And it also has a very unique tidal regime. And we are expecting, with climate change, a change in these tidal regimes in the Solent region. So it's an interesting area to assess impacts of climate change in seagrass, carbon storage, and sequestration. So here are my study sites within the Solent. I actually have 6 study sites, and I have one here in Portsmouth Harbour, which represents a study site with mud substrate. We have the Solent is also interesting because it has a wide range of different substrates. So in Portsmouth, I have mud substrates, and I also have one of the biggest harbours in the UK. So I have a lot of anthropogenic activity. In Langston Harbour, I have 2 sites. One is saltmarshes, and the other is, I actually call it Langston, But the Farlington Marshes one is actually very exposed as well to anthropogenic activities right by the side of the road. And the Langston one, which is more or less here, is a little bit more sheltered. I also have a Chichester site, which is it's represented by actually very sheltered estuary. And I have two sites on the Isle of Wight, which represent my sites with sand substrate. And they are more exposed to waves activity and also anthropogenic threats. So here are some of my results. Like I said, I'm showing some of my preliminary results. And these results here are just for below ground organic carbon. So I have assessed soil organic carbon. My soil cores were collected down to 1 meter deep. Only one site I couldn't go down to 1 meter depth, which was Cowes in the Isle of Wight, which I hit refusal up to 20 centimeters. I hit gravel. So there was no soil layer below that. But all my other sites, I went down to 1 meter deep cores. And I assessed percentage of organic carbon using loss and ignition. And below ground biomass, I assessed using a separate cores, which I collected down to 50 centimeters to separate below ground biomass. This total below ground carbon pool was assessed using an estimated area of coverage, which is the latest estimated area of coverage given by the Wildlife Trust. It's a survey that's been done about 3 years ago. And this was done in the summer last year. So in the summer this year, I'm also going again on site, and I will do drone surveys and also walk around and try to measure the area so I can have a more accurate extension of my sites and not just by estimation. Here you can see grouping results of the variance between soil organic carbon from my sites. And what is interesting in the grouping is that my two most sheltered sites are significantly the same. They don't have a lot of significant difference. And my two more exposed to wave activity sites and the sand substrates, which are the sites in the Isle of Wight, are the ones with lower organic carbon in the soil. This graph here shows the relationship between soil organic carbon and below ground biomass, so roots and rhizomes. Again, you can see here using a coupling, the coupling analysis, that the sites with more wave exposure, which is the Ryde Isle of Wight sand substrate site, has a higher below ground biomass percentage than the other sites. This site here actually has an activity of hovercrafts that comes every 15 minutes, big hovercrafts bringing passengers all the time. So it's very exposed to wave activities, sand substrate, and also anthropogenic stress. The most sheltered sites, which were the ones with higher soil organic carbon, are the ones with lower percentage of below ground biomass. In terms of dry bulk density, we have a very similar grouping to what we had in soil organic carbon, but in an inverse way. So the sheltered sites are the ones with the lowest dry bulk density, whilst the most exposed site is the one with the highest dry bulk density. So to assess carbon sequestration rates, I used 40 centimeters to 40 centimeters cores per site. And they were, today I'm bringing to you 4 results from 4 sites. And they were analyzed for excess lead to 10. So it's the excess lead to 10, we say it's excess because we are analyzing what we assess as a fallout from atmospheric fallout from the decay of radon-222. But we also have to take into account the in situ lead-210, which is the one that should be present in the soil, and it comes from the decay of radium-226. Decays into lead-214 and should be in the soil, which is our supported lead-210. So here, there is a down-core profile of my lead-210 data for the 4 sites. And in this slide here, we have one of the models that you can use to assess, to generate sediment accretion rates using lead-210, which is the constant flux, constant supply model. This model here assumes a constant rate of sedimentation. And for the 4 sites, it gives you an average of accretion rates by giving you a plot of the natural log of the excess lead-210 against depth. You can see a high variance in average here. And again, this is because this model assumes a constant rate of accretion rates, and that might not be the case for my sites. This other model here, which is the constant rate of supply model, actually dates the sediment and provides a sedimentation rate per age of the sediment. And to do this, it takes into account excess lead-210 and dry bulk density. So you can see here, for this model, only 3 of the cores were applicable. So here, in terms of sequestration rates using the CRS model per year, you can see that you will find peaks and dips in the graphs. And here is the average calculated sequestration rates for the 3 sites using the CRS model. What I propose in my project is to explain how climate change events and extreme weather events can be related to these peaks and dips. In order to do this, I will look into a very wide meteorological data, and I will look for flooding events, storms, sea level rise, and other environmental aspects that I'm still collecting. And I will analyze and see what could be impacting, what could be causing these changes in sequestration rates. On a very basic Google search, I found a few reported extreme weather events that could be well related to these dates here. So flooding events in 79, great storms of 87, drought in 76, or the storms of the century in 53. So this was a very basic Google search just to see if I could find anything that could be related to those dates. And this is what I found. So to conclude, based on my results in terms of carbon storage, I can say that UK seagrasses are very important in carbon sinks potential, and they should be included in climate change mitigation strategies, and understanding how carbon sequestration rates can change with climate change events is very important, so we can think about the future and how we are going to include them in strategies. So, thank you.
Thank you, Mariana. Any questions, Barry?
Yeah, my specialty is actual new chronology that you talk about. It's not the methods of conservative supply, whatever, are not given that there is a constant rate of supply. So the way, if you look at the Amaral's work, it's not the default, it's actually regarded as the exception. And these methods, these common methods like CIC, which is the other one, or conservative supply, are mapping methods in which you cannot validate the model by the shape itself alone. You can get different values out of different shapes, or the same shape, with different rates of supply and different sedimentation rates. So you need a validation of the model. Traditionally, it's been for CRC, it's quite good because it's an inventory component. You use something like cesium or an event. Because what happened, unfortunately, in seagrass literature, I got to talk to one of our previous speakers who searched it. I have not seen any validated seagrass lecture-being chronology. I don't know if it's correct. A lot of times they don't even present the data. They say you use this model without actually looking at it. So validation is extraordinarily important. the whole basis of your reconstruction is the certainty that you have got the model correct.
Mhm.
It's easy to fit data. If there's something which is wrong, you get a story. It's important. It's horribly easy, unfortunately. So there are other models which are more horrible to use. There's one very rarely used, which I use, which is an inversion model, which actually models the profile, which we'll talk about in the next section, called sediment isotope tomography. And it has no assumptions on what if it's once constant or not constant.
Yeah.
So it's just a warning for people who are doing this work in seagrass alone. As Appleby said, which you know, it is not a standard process. It is hard. And the other thing to consider when you look at the profiles, look at the geochemistry. When you say you've got floods, I've got a paper last year in policy looking at floods and estuaries, and not only these floods deposit sediment at instantaneous events, which you've got to conceptually remove to the baseline sediment, so you get that much reduced in an instant. The model cannot take account, but also you can get erosion, which is a more difficult thing. So validation of these things is so important because, quite honestly, I don't know if the world average is actually correct. I just don't know. It's opaque, the data, and the methods have never been validated. So I just put that as another crusade. I'm sorry. I feel like I'm flashing the drum a bit in blue carbon science. So mangroves fine. You see a lot of season work, but not actually season.
You know, actually, I couldn't detect season.
I know it's a
yeah.
you can't do. So you have to look something else.
Yeah.
And you'll use your imagination in theory work. It's like it's like Sherlock Holmes. It really is a detective story.
Yeah.
Which is part of the fun.
No, thank you so much. I brought this here as we are working on it, just to see suggestions and see what we can do about it. But
You can maybe give some ideas tomorrow when I've got some data on SIP.
yes, thank you. That would be lovely. Thank you.
So I think we are running out of time. Thank you,
Thank you.
Mariana. So let's give a hand for